Okay everyone, I'm just going to do a video on kinematics, and it's this part of the lesson which I know many of you are not very sure about when I talk about the gradient component. And this is essentially the mathematics perspective of what we are doing in physics. Okay, so I'm not going to go through this in class anymore, but I thought I'll just do this video so that you can just look at it in your own time and just take reference from there. Okay, so what's this gradient understanding of kinematics graph all about? So in lesson we start off with a displacement time graph, and you know in displacement time we use S and not D, and this is your time. And then I can just make this a little bigger for you to see. Yep, okay. Okay, so we talk about displacement time, and let's just take a very simple example, and that is your displacement time. And when you draw this, we have already discussed this in class, and you know that the motion is at rest, all right, not moving. And if you were to plot or to sketch a VT graph, a velocity time graph, you will have a flat line right at the bottom, because we know in physics we say when it's at rest the velocity is 0, right? 0 meters per second. So the graph will look like this at 0. Now, how is the gradient of this equivalent to this? To illustrate this point, I'm going to talk about another graph which you're now very familiar with, is this upward slope graph. And in our discussion, this is known as constant. The motion is known as constant velocity, which means that the vehicle or the particle is moving with a constant speed or a constant velocity if you're talking about vectors, all right? So constant speed. So how does this translate? And this goes straight line. Okay, so why do I say that this gradient will give this? So to understand gradient, we must understand what this is all about. So in mathematics, this, if you were to plot as a y-axis and x-axis, the equation of the graph will give you y equals to mx plus c, right? Y equals to mx plus c. This is the y-intercept, and this is the gradient. This is that general formula for a straight line graph. In this case over here, your y-intercept is 0. So essentially this gives you y equals to mx plus 0, right? So which means that your m is y over x. So y over x is the gradient. So, or some of you prefer it to y2 minus y1 over x2 minus x1. It's essentially the same thing. All right? This is in the coordinate geometry. So when you do y2 minus y1 over x2 minus x1, what you have is this component over this component, the gradient. So it's y over x, y2 minus y1 over x2 minus x1. So that's the gradient. Now if you were to bring this back up, so this gradient is essentially your y over x. I'm going to use a different color now. Now what is y here in this graph? What is y? Y is actually the displacement in meters. See, this is meters. And this x is essentially your time. in seconds. So the gradient is y over x, right? The gradient is y over x, meters over second. So your gradient is y over x is meters over second. This is essentially your velocity. So the gradient of the displacement time graph will give you the velocity. And over here, the gradient didn't change. It is a constant gradient. It is a constant gradient. There's no curve, nothing. It's just straight, constant gradient. So this is a constant line throughout. So if the gradient here is 5, then your velocity here is 5. So let's bring this up again. It makes sense because now your gradient, there is no y. There is no y. The y didn't increase. Y remains the same. The y value remains the same. The meters remains the same. So it's essentially 0 divided by a time, x1, x2. So it's over x. Anything divided by 0 divided by anything will give you 0. So therefore, this is 0. The gradient is 0, and it's actually 0 meters per second. So this understanding is by using a very mathematical approach where you talk about the gradient of the displacement time graph will give you the velocity time graph. Okay, I'll give you one more last example and you see how this might change. So let's look at the more complicated one where we look at this curve. And in our discussion in class, I told you how the displacement changed with time. This is actually a increasing velocity. Okay, it's getting faster and faster and faster because as time goes by, it's able to cover more displacement. All right, we've done this discussion already in class. So using a mathematical approach, how will the gradient of this graph gives you the velocity time graph? So let's look at the mathematical approach, okay? The gradient, now this is not the same gradient, it's not a constant gradient anymore. The steepness, the gradient changes. Over here is constant, So it is just constant, it's not changing. But over here, you can see that it's changing. All right, so I'll just use something to help. Okay, never mind. Yeah, I bookmark. Okay, see. So the gradient at every point, in the graph increases. I'm not talking about the value increases, I'm talking about the gradient. So the gradient at this point is this. The gradient at this point is this. The gradient at this point is this. The gradient at this point is this, and so on and so forth. So you can see that the gradient slowly increases. The gradient here is the same throughout. The gradient here is increasing. So when the gradient increase, initially it's flat, so it's 0. As the gradient increase, the gradient of the displacement time graph gives you the velocity time graph, and over here the gradient increases, so the velocity increases in a straight line. And it's true, it's increasing velocity. In fact, I told you that this is known as a constant acceleration, increasing velocity. All right, so I hope you appreciate this approach of using the gradient component or the gradient analysis to understanding this. Okay, stretching this further, Stretching this further, how is the gradient of this? You realize that the gradient is constant. It's constant. y1 minus y2 minus y1 over x2 minus x1. Your gradient is constant. It's not changing. It's a constant gradient. Constant gradient. Right? So the gradient is constant. Using this idea, what can we plot now? All right. Okay. So the gradient of the velocity time graph is essentially y over x, and over y here, I use my blue pen because previously I used my blue pen for the units. So y units is actually meters per second. Divide by the time. Divide by second. Meters per second over second, if you work it out, is actually meters per second square, and this is essentially your acceleration. Your acceleration. So the gradient remains constant. The gradient remains constant means my acceleration time graph, I should have a constant value. And it's true, constant acceleration. Okay? So, in summary, the gradient of the displacement time graph gives me my velocity time graph. The gradient of the velocity time graph gives me my acceleration time graph. All right. So if you appreciate this idea about the gradient, you begin to understand how the three graphs actually matches. Okay, this is pretty high level, but I hope you see that link between mathematics and the physics part. Okay, all right, see you.